Hey, thanks Barry, thanks everyone for joining. So today I'm going to talk about a new fully homomorphic encryption scheme, which we call the Generalized BFV scheme, and this is joint work together with Free. To motivate this presentation, I would like to start by making a comparison between two FHE schemes that already exist today. So in FHE, we want to compute unencrypted data, and there's multiple ways to do this. In the BFV scheme, the idea is that we will compute over some typically very small finite field, so a finite field of small characteristic p. Then there's also another scheme known as CLPX, where we will compute over a quotient of the integers modulo some huge p. Another difference is that the BFV scheme can encode multiple of these finite field elements into a ciphertext, and in the presentation this will be visualized with these kind of hypercubes. So in this toy example, we can pack 8 slots. Moreover, the BFV scheme can compute arbitrary computations via bootstrapping. In CLPX, there is no efficient bootstrapping. And then here I give you some example parameters. So just to give you an intuition, in the BFV scheme, we could encrypt 1,200 finite field elements. In the CLPX scheme, we could be working with a characteristic that is this 2 to the 14-bit number here. So note in CLPX, this p is really a huge number. Now, it turns out in many practical applications, we would like to have some FHE scheme that lies between BFV and CLPX. So a scheme that can compute over a finite field of relatively large characteristic, that can also pack multiple data elements, and that can be bootstrapped for arbitrary computations. And as you may guess, these research questions are solved by our generalized BFV scheme. Okay, let me introduce a couple of notations. We will be using ring learning with errors, so we will use cyclotomic polynomials. This is this phi m of x here. And then the corresponding cyclotomic fields and rings will be written as k and r. All our computations will happen over a ring that we call the plaintext ring. To do that, we select some non-zero element of our r, which we call the plaintext modulus, and we write it as t in this presentation. And then the operations will happen over the quotient ring modulo t. Okay, so in summary, we have two moduli here. One of them is the cyclotomic polynomial, and the other one is the plaintext modulus. I will again explain our generalized scheme via comparison to previous schemes. Let us start with BFV. So recall in BFV, the idea is that we want to compute over small finite fields. So suppose we want to compute over fp. Then the idea is simply to take the plaintext modulus equal to p and encrypt using some ciphertext modulus, which is necessarily much greater than p. And CLPX overcomes this previous limitation, and it uses a clever trick to do this. So in CLPX, we take the plaintext modulus not as an integer, but as a linear polynomial x minus b. Now, as a result of this special shape, we can simplify the plaintext ideal. So since x minus b is in the plaintext ideal, we actually have that x is equal to b in this quotient ring. So as a result of that, we may substitute x with b everywhere. So we get this, instead of the cyclotomic polynomial itself, we get its own evaluation in b. As a result, our plaintext ring basically provides native arithmetic modulo this integer phi m of b, which we renamed to p here. Okay, earlier I gave this parameter example where we had this huge value for p here. And here in this box, you can see that we indeed overcame the BFV restriction since p is greater than q, which is simply impossible in regular BFV. Our generalized BFV scheme is a unification and generalization that covers both BFV and CLPX. In particular, we support arbitrary non-zero plaintext moduli. Now, I have to say that the encryption and decryption generalize pretty trivially, so they will not be the focus of this presentation. Just a quick summary. So here we also use ring LWE encryption, and in the presentation, I will write such encryptions by writing our plaintext in the green region here, and then our noise in the yellow region. And as usual in FHE, this decryption works correctly as long as the message region and the noise region do not overlap. One very important functionality that we need in the generalized BFV scheme is a function that computes representatives modulo t. For this, we introduce a new function that we call flatten, and the definition of which is written on the top of the slide. Okay, so the idea of flatten is that the output will have small coefficients. When we do the analysis, it turns out that the norm of the output depends on two things. One of them is the cyclotomic ring that we compute in. This is the red vector on the slide. And the other one is the size of the plaintext modulus that we use. And from this inequality, you can see why using plaintext moduli of small norm is interesting, since this will decrease the flattening bounds. Okay, let's make this a little bit more concrete. So in the case where t is an integer, when we are working in regular BFV, then flattening will simply correspond to a coefficient-wise reduction. In this case, the input will be reduced modulo 5. So each of the coefficients is reduced mod 5. If t is a linear polynomial, in this case x minus 4, then flattening will correspond to a base 4 expansion. So we substitute 4 with x everywhere. But flatten can also be defined for more general moduli. In that case, we still have an output with small coefficients, but there is not really such an interpretation of it anymore. Okay, so the goal of FHE is computing unencrypted data. In this slide, I will be treating the case study of a homomorphic multiplication, where we are interested in multiplying a ciphertext together with the plaintext. To do that, we first flatten the plaintext. This gives us some alternative plaintext m hat, and then multiply this coordinate-wise to the ciphertext. Okay, illustrating this on this encryption diagram, what we see is that the output ciphertext indeed encrypts the product of the two plaintexts. But as usual in FHE, our noise of the output will get slightly larger than the input noise. For correctness of decryption, it's important to have a tight estimate on this output noise. It turns out this output noise depends on two things. One of them is the size of the input noise, and the other one is the flattening bound from the previous slides. And again, from this inequality, you can see why using t of small norm is interesting, since this will decrease the noise growth in FHE. Let us now study the plaintext space of our generalized BFV scheme. And to do that, we start from this identity, which holds in general for cyclotomic polynomials, and we just listed on the top of the slide here. In contrast to CLPX, we take our plaintext modulus as a nonlinear polynomial, which is x to the k minus b. And then we use a similar trick to simplify the plaintext ideal. So in this case, we don't substitute x for b, but we substitute x to the k for b. If we do that, we get native arithmetic modulo this integer, phi r evaluated in this power of b. And if this integer is a prime, then we call it a cyclotomic prime because it's obtained by evaluating this polynomial, this cyclotomic polynomial in an integer. For the rest of this presentation, we will indeed assume that b is prime. Okay, this slide considers one specific example of such a cyclotomic prime, which is the prime 2 to the 16 plus 1, which is also known as a Fermat prime. First thing I want to mention is that this prime is not achieved for a single plaintext modulus, but for a whole range of plaintext moduli, a whole family of plaintext moduli t of x, depending on the parameter I here. And then it turns out that each of these different i's gives you a parameter set with different properties. And this is well illustrated in the table. For example, if we consider this left column, we have a parameter set with a small number of slots, but also very small multiplication noise. On the other side of the table, we have a parameter set with a larger number of slots, but also much more multiplication noise. So you can basically see this as a trade-off where you can really precisely set the number of slots that you want, and based on that, you get either slower or faster multiplication noise. Another interesting prime, especially for zero-knowledge applications, is this 64-bit Goldilocks prime, which you can see on the slides. Here we can make a similar table with the same conclusion, namely we have this trade-off between slots and between noise. But for the Goldilocks prime, the gain from using GBFV is even higher, since this leftmost parameter set has 7 times smaller noise than the rightmost one. Okay, now I would like to talk a little bit more about this ciphertext packing and this hypercube structure. And I will start with a regular BFV example. So in this example on the slide, we see a 3 by 3 by 4-dimensional hypercube. And the idea is that each of these mini cubes here encrypts one finite field element. One important operation in BFV is that we can map, permute these plaintext slots. And on the hypercube, these permutations act as one-dimensional rotations. So here, for example, we see a rotation in the vertical dimension where each slot is mapped up with one position, and then the top slots are moved back to the bottom. Now, with generalized BFV scheme, we have something similar, but recall that we have a smaller number of slots. Because of that, only a subset of the slots in our hypercube can still encode data, and those are the slots in green on the slides. The red slots can simply not be used anymore. Because of that, we also need to be very careful when implementing these rotations that we always map green slots to other green slots and not a green slot to a red slot, since the red slots do not contain any data. One interesting operation that we have in the BFV scheme already, and which we would also like in the generalized BFV scheme, is ring switching. In ring switching, the idea is to change the cyclotomic ring during the computation itself. If we illustrate this on the hypercube diagram, what would happen for generalized BFV is that we process this larger hypercube to a smaller one. But as a result of that, also the number of slots reduces from 2 valid slots to only 1 valid slot. Another interesting operation for bootstrapping in particular is converting a GBFV ciphertext to regular BFV. Now I will just explain this on the hypercube. So here we start from a GBFV hypercube where only 2 slots are valid in this example. And then we process this to a fully defined BFV hypercube. Then the slots that are green here on the left will just be copied to the right. The slots that are red here on the left will just contain garbage value on the right. Now, the conversion routine from the previous slide doesn't really use the available BFV space efficiently, since there are many of these garbage slots. And therefore, we also propose a conversion routine a packing routine that packs multiple GBFV ciphertexts into one BFV ciphertext. Here, the idea is that we will start from multiple hypercubes. So in this example, we have 2 GBFV hypercubes. Then for each of these hypercubes, we will run the conversion routine from the previous slides. Then something else that we need to take into account is that for the second hypercube, we need to map each slot to the left with one position so that they will not interfere with the slots from this first hypercube. Now note here that it seems that I am violating one of my own rules, since I am mapping a green slot to a red slot here. But actually, this mapping comes after we have already converted to BFV. So at that point, this mapping is allowed. Then we add everything up, and this gives you one nicely packed BFV ciphertext. For our GBFV scheme, we also introduce a bootstrapping operation. So in FHE, each operation has a certain amount of noise accumulation. And in bootstrapping, the idea is that we will reset this noise to a predefined level by homomorphically decrypting. Now, due to technical limitations, we were not able to instantiate all of our steps in the GBFV scheme directly. So as you can see in this diagram, we also rely here on conversion from GBFV to regular BFV. And some of these steps here in the bootstrapping are evaluated in the BFV domain, but then the final step is again evaluated in GBFV. We implemented this bootstrapping in the Microsoft C library, and this table shows some results that we got. An important difference with previous works is that we can instantiate our bootstrapping with much smaller parameters. In particular, we only use the 2 to the 15 cyclotomic ring for 128-bit security. The reason that we can use these smaller parameters is that our scheme has smaller noise growth. In total, we can bootstrap a ciphertext in only 2 seconds, which is roughly 5 times faster than regular BFV bootstrapping. And then another interesting line on this table is this remaining noise capacity, which basically models the room that you have left for further computation before you need to initiate the next bootstrapping. Also on this line here, you can very well see the trade-off between slots and between noise. For example, in this left column, with a small number of slots, we have a large remaining capacity. But in this right column, with a high number of slots, we have small remaining capacity, which is due to more noise blow-up in the bootstrapping itself. Okay, so to conclude, this presentation proposed a better way to instantiate these large cyclotomic prime fields in FHE, where we have this very flexible trade-off between packing and noise. And we also have this lower latency bootstrapping because of less noise growth. Yeah, and then bootstrapping crucially relies on this conversion routine to the regular BFV scheme, since we do not know how to instantiate some of the steps directly in GBFV. Okay, I would like to end with this QR code. So behind this QR code, you can find a blog post that I wrote about the paper. So if you're interested in the paper and you would like somewhat more lightweight reference, then I recommend the blog post. Okay, thank you for listening.